Hello, welcome back. All right, today we're going to look at forces because it relates to that hammer question that you received from the ministry. Okay, so we have to look at forces before you're able to answer that. So basically, a force is any vector that is acting. So a force is any vector which is directional that is acting on any object. Now it has two consequences. It can deform the object, or it can change its movement. Okay, so one example would be if a golf club hits a golf ball. The first thing it does is it squishes the golf ball before it launches it out. So it deforms it, and then it launches. It's a temporary deformation, but it deforms it and then launches back out. Another way is if a car is driving along and it speeds up or slows down, that's a force vector acting upon it. Even changing directions, to turning left, turning right, you have a force acting on it. So that's the two things that a force vector will do to any object. Okay. Um, Force is measured in newtons. Okay, so any force vector is measured in newtons, and 1 Newton is equal to 1 kilogram meter per second squared. Okay, so it takes into account the weight of the object, the length of the distance, and the speed, the time, right? Meters per second squared, and the weight of the object. Okay, and we use dynamometer to measure. So this is basically anything attached to a scale, a spring. So if you have a hook like this, a spring, and then another hook right here, and then as you pull it down, it has a little gauge. So the gauge should be here, and it has all these numbers. So as you pull it down, you hang something to it, and you pull it down, this thing comes down or it goes back up, and this is measured in newtons. This is much the same as the scale that you might have in your bathroom. So you step on it, right? So it has numbers up here. Inside is a spring, and then you step on a platform. As you push down, the scale moves left or right. All right. Okay, and then so that is basically the definition of what a force is. We've been doing force vectors as soon as we started drawing vectors. Okay, so then we get into gravitational force. Which is Fg, because of the vector, there's a little arrow above. Gravitational force is the attraction between two objects of masses. In other words, any two objects that have a mass, no matter how small or how big, those two objects will be attracted to each other. Okay, so this is the one that Newton sort of calculated when he realized he sat, the whole Newton story. He sat under a tree, and then an apple. He was reading, an apple bonked him on top of the head, because the apple has a mass, he has a mass, the earth has a mass. It fell down towards the earth and bonked him in the head, and he came up with the gravitational force theory, and then he came up with an equation to come up with that. So he said force of gravity is equal to the gravitational constant times the mass of the first object times the mass of the second object times the radius between them squared. Okay, so G is the gravitational constant, and he would calculate it to be 6.67 times 10 to the negative 11. That's supposed to be 10 to the negative 11 Newton meters squared per kilogram kilogram squared. Now the units are this way because they cancel each other out to end up with newtons at the end. Okay, and then mass, obviously mass of the first object. Mass 1 is in kilograms. Mass 2 is also in kilograms, and radius is measured in meters, right? So this is the distance between them. The distance between them. That's the mass of the first object, second object, and that's a gravitational constant. Obviously, this is a gravitational constant on Earth. If you go somewhere else, it's a different number altogether. All right? Now, in the textbook, what page is it? In the textbook, on page 268, example A and B, you'll get to see a couple calculations happening, a couple examples that will take you through the calculations so that you can learn how to use these, right? I'm not going to take the time right now to do them because you can see them in the text now that you have access to the text. Oops. All right, and now look at gravitational acceleration. Or little g. So gravitational constant was big G, gravitational acceleration is little g. We've been using this one for a while when we started looking at UARM and projectiles. It's basically how fast does the Earth speed up any free-falling object, right? So we know that if an object is in free fall, it speeds up the longer it's in free fall because the Earth has a big mass and it is drawing it. It is speeding it up. It is causing a force vector upon that falling object towards the Earth. Now we know that G is equal to 9.8 meters per second squared. Okay? And that two objects, regardless of their size, will fall with that acceleration in a vacuum. So obviously, if there's no air resistance whatsoever, a bowling ball and a feather will fall towards the Earth at 9.8 meters per second squared. The only reason that we see a difference is that the feather is creating more susceptible to the air resistance as it hits through it. The air is slowing it down just because it is lighter compared to the air. But if there's nothing stopping and there's nothing else in the way, the bowling ball and feather will fall down at the same speed. All right, and we use 9.8. This is accepted because most of the experiments that we're doing are at sea level. Obviously, if you go to the top of a mountain, so if we have a mountain here, the sea, and then you go down. Let's say you have a submarine down here. Here, it is at 9.8 meters per second. Here is going to be less than that. And down here, it's going to be greater than that, right? Just because of the distance from there to the center of the Earth, right? Because we said that the gravitational force, I don't know if I said before, the gravitational force, the G m1 m2 over r squared, says that it is inversely proportional to the distance, meaning that the further away that they are, the less force they attract upon each other. The closer together they are, the greater force they attract. And so the submarine is closer to the center of the Earth, and therefore it is going to have a greater attraction force, which means it's going to have greater acceleration due to gravity. But at sea level, which is where we are going to use 9.8 meters per second squared. Okay. And then we get to force of gravity, Fg. So force of gravity on any object is how hard the earth is pulling upon that object, right? It is based on the earth pulling you down. Okay, so it is measured, again, it's a force, so it's measured in newtons. And then you have force of gravity is equal to the mass times the gravitational acceleration. Okay, so if you put in, so 75 kilogram man standing on the sea level times 9.8 gives you whatever the answer is, right? What is that? Just under 750, 740, 735. 735 newtons. Okay, kilograms per meters per second squared, which is what a newton is, right? So that's how you calculate how much force is being pulled down on any given object. So if you have a person, 75 kilos, that is the FG. So the FG for this person, 75 kilos, is 735 newtons. Okay, now this is the weight. So this is the weight of the person. Weight is relative to how hard the earth pulls down upon you. The mass of this person is 75 kilograms. Okay, so when you step on a scale, you're actually getting your gravitational pull. Okay, because that what the scale is showing you is the amount the spring is compressing. Remember we talked about that before? The spring is compressing when you step on it, and therefore it is measuring this. Okay, so it is measuring gravitational force upon you when you step on that scale. It is not measuring a balance. It's not measuring your mass. Okay. So for example, if the same person, 75 kilograms on Earth, has 735 newtons, on the moon, that person will still have the same amount of mass. In other words, what they contain is still the same amount of muscle, bone, water, whatever you call it. However, if they step on a scale on the moon, they're going to be weighing a lot less, just because the moon's gravitational pull is much lower than the Earth's gravitational pull. All right. Okay. And then normal force. So normal force, Fn. Normal force is basically what keeps an object in its place. So right now, the fact that I'm standing here on the ground and not sinking closer towards the center of the earth. Now, if I'm standing here, the earth is pulling down at me. Now, I'm slightly more than 75 kilograms. Let's say my Fg is 800 newtons. Okay, the earth is pulling down 800 newtons, so I'm standing right here. The fact that if I only have one force pulling down, I should be sinking, as we were talking. I should be getting lower and lower and lower into the ground. But I'm not, because the ground itself is exerting a force of 800 newtons upwards at my feet, keeping me upright. That force is called the normal force. Normal means 90 degrees, right? Perpendicular. So perpendicular to the ground that I'm on. So if I'm standing on the ground, the force is going this way. If I'm standing on the wall, the force would be going this way, right? Perpendicular to the ground or the surface. Okay, every object that is stationary, Fg equals Fn. So you don't have to do a whole set of different calculations to find Fn. If you can use Fg equals mg, you get the same thing as that. Okay, so once you know the mass, you know if I'm stationary, you know that my Fn is going to be exactly the same as my Fg. However, if I'm sinking, then you have to consider the rate at which I'm sinking to figure out the Fn. Okay, because you can use acceleration in there to find you're changing your g, right? velocity 1, velocity 2, going all back to that. But we're not going to get that complicated. All right, and then frictional force. F. So force of friction is the amount of force of two things wanting to, when they rub against each other, right? So if I have a heavy box like this on the ground, the interaction between them is called friction. Okay, so some objects are harder to push on different surfaces. So if I had a giant box of 100 kilograms and it's on asphalt, it'd be pretty difficult to push. However, if I take that same 100 kilograms and I put it on ice, automatically it becomes easier to push. And not because ice is cold or ice is slippery or wet or anything like that. It's just simply because of the interaction between the box surface and the ground surface. Okay, every surface exerts its own coefficient of friction. So it's called U. So every single surface has its own coefficient of friction, right? And in your textbook, it has a big huge list on it. Page 276. It has a whole list of different types of surfaces and the amount of coefficient that friction has on there, on any object. Now, there's also static friction and kinetic friction. Okay. Now, this goes back to Newton's first law, second law. Anyway, an object in motion wants to stay in motion. An object at rest wants to stay at rest. So if it is staying at rest, if it's just sitting there, static friction exists between the two objects. In other words, it wants to stay in that spot. You have to put enough force into it to make it start moving from that spot. Okay, so that is called static friction. How much resistance you're getting to keep it in place. Okay, kinetic friction is once you get it going, how much do you have to put in to keep it going? Well, this number is going to be less than this number. Okay, so if I have a box sitting on my hand and I want to get it going, I have to push with that much force. But once I push that much force, I actually need a lot less. Well, not, I shouldn't say a lot less, but I actually need less force to keep it moving than when I got it started. It's always tougher to get it started than to keep it going. Okay? Right before it moves is when static friction is at its highest. The instant before it starts moving is when static friction is at its highest, because you've now taken, let's imagine like these are all like little tentacles keeping it in place. So as I push it, tentacles are stretching. So right now I'm pushing pretty hard, then all of a sudden, oh, the tentacles break and I'm going. But if I stop pushing, the tentacles will grab on again. Okay? So static friction is what's keeping it in place, and kinetic friction is what's going keep it moving. What do you need to do to keep it moving? Okay? And you calculate friction force by the coefficient times the normal force. Okay? And the normal force is Newton's third law, where it says every object has an equal and opposite. Every action has an equal and opposite reaction. Gravity is the action. Normal is the reaction. So if you take the reaction, times it by, because that's what's holding it up, right? The reaction. So, and it goes. All right? So that is frictional force. And the last force we will look at for this session is going to be tension. And not the tension that you have right now because I'm flying through this lesson. All right, so tension, Ft. So tension exists when two objects are, or an object is being held via a rope. So instead of sitting on the ground, you now have this box and it's being held up by a rope, let's say. Okay, holding the rope with the pulley there. So this force is the tension force in the rope. Okay, it is two directional, boom, on the same object. So you have tension force there and Fg here. So whereas before you had Fg here and Fn sort of coming from the same point, right? Where here you are now in two different directions. So Ft is the same as Fg. Again, if you are keeping it in place, if I'm just holding the box up in the air without moving it, these two are the same. Otherwise, that one's greater if the box is going up. This one's greater if the box is coming down. Okay? So that was a lot of information because we only have one physics lesson this week. So I'm going to upload all the questions for each one of those forces onto a different document. Click on a document, you'll be able to download it and then do all the questions there. All right?